on the morning of 15 November 1988, a 60-meter-long Soviet spaceplane came screaming back into the atmosphere over Kazakhstan, and no one was at the controls. At Baikonur Cosmodrome, wind crawled across the flat steppe and tugged at the concrete runway, but the vehicle called Buran lined itself up, flared, and touched down with a precision that would have been impressive for a veteran test pilot, let alone a machine that had just come home from orbit, completely alone. That single landing, unmanned, automatic, and performed under conditions that made ground crews uneasy, was the kind of result the Soviet Union lived for in its final years. Spectacular, expensive, and almost unreal, it was also the endpoint of a much longer story, one that ran on fear, rivalry, and an almost stubborn faith that if you pushed hard enough, if you built big enough and tested ruthlessly enough, some of your strangest ideas would stop being fantasies and start being hardware. The Cold War is remembered for standoffs and speeches, for spies and nukes. Less often do we remember it as an age of experiments so bizarre they sound like rumors. Yet some of those experiments didn't just kind of work. They worked measurably, demonstrably on the record, sometimes so well that even their enemies quietly took notes. Because if you want to understand the Soviet 20th century, you can't just look at ideology. You have to look at the laboratories that smelled of hot oil and ozone, the design bureaus where men in wrinkled suits argued over engine thrust and materials science, the frozen seas where nuclear reactors drove ships through ice, and the distant planets where Soviet landers took pictures in a sky that was literally toxic. These were not fairy tales. They were dated, logged, numbered, launched, and sometimes recovered. And in more than a few cases, they were terrifyingly effective. The first thing to understand is that the Soviet experiment was rarely an experiment in the casual sense. It was usually an experiment under pressure from the party, pressure from the military, pressure from rival design bureaus, and, most of all, pressure from the United States, whose own technological leaps were treated in Moscow not as news, but as threats. That pressure produced a peculiar Soviet pattern. Pursue multiple approaches at once, hide failures behind secrecy, and when one approach works, present it not as a lucky break, but as proof of the system's destiny. Yet the hardware doesn't care about propaganda. A wing either produces lift or it doesn't. A radio signal either returns from interplanetary space or it vanishes into noise. A reactor either powers a ship or it becomes an emergency. And in the space between what the Soviet state promised and what physics allowed, a handful of bizarre projects did something rare. They crossed the gap. In the early 1960s, one of the most improbable Soviet projects began to take shape not on a launch pad, but on water. The Caspian Sea, stretching like an inland ocean between Russia and Iran, became a hidden proving ground for a craft that seemed to mock the rules of flight. The concept was called the Ekranoplan, literally screen plane, a vehicle designed to skim just above the surface, exploiting the ground effect that reduces aerodynamic drag and increases lift when a wing flies close to a flat surface. Ground effect is something pilots notice when landing an aircraft that floats a little before touching down. Soviet engineers looked at that subtle effect and asked an outrageous question. What if you built an entire war machine that lived inside that cushion of air? The man most associated with making the Ekranoplan real was Rostislav Evgenyevich Alexiev, a brilliant engineer already known for high-speed hydrofoils. In the West, rumors started to circulate when American reconnaissance satellites photographed something enormous moving on the Caspian. NATO analysts gave it a nickname that sounded like pulp science fiction. The Caspian Sea Monster. The vehicle they had spotted was the KM, an experimental Ekranoplan that first flew in 1966. It wasn't a small prototype. It was a monster in the literal sense, about 92 meters long, with a maximum takeoff weight reported around 500 tons. It roared low over the water on multiple jet engines, moving faster than most ships could ever dream of, while staying below many radar horizons and, at least in theory, below the engagement envelope of certain weapons. For a time, it looked like the Soviet Union had invented a new category of strategic weapon. Not quite ship, not quite aircraft, but a fast, radar-hugging creature of the sea. The weirdness of the Echronoplan wasn't just its shape, it was the way it blurred military assumptions. Navies are built around prediction. Ships are slow, aircraft are fast, missiles are faster. The Echronoplan was fast like an aircraft but moved like a ship, able to carry heavy payloads, theoretically capable of skimming under radar and striking with little warning. It made traditional categories feel obsolete, and that alone made it valuable in the Soviet system, which thrived on asymmetric answers to American advantages. The Echronoplan program did not remain a mere spectacle. In the late 1970s and 1980s, the Soviets produced operational designs, including the A-90 Orleanok troop transport and the Project 903 Lun-class missile Echronoplan. The Lun, first launched in 1986, was armed with 6 P-270 Moskit anti-ship missiles mounted like a brutal crown on its back. Imagine for a moment what it meant: a missile carrier that could sprint low over the sea at hundreds of kilometers per hour, carrying a heavy anti-ship punch designed to kill vessels that cost more than the Echronoplan itself. Not every claim made for these machines held up, and they were complex to operate, sensitive to sea state, and expensive. But they did the one thing skeptics said they wouldn't. They flew, they carried loads, and they became, in limited numbers, real military assets. The experiment worked, just not enough to reshape the world before the Soviet Union ran out of time. Far above the Caspian, another set of Soviet experiments was unfolding that felt even more surreal: war machines designed to operate in orbit. The Cold War turned space into a mirror of earthly paranoia. If the United States could put reconnaissance satellites overhead, then Soviet planners imagined weapons platforms. If America could develop the space shuttle, Soviet planners imagined that it might be used to deploy or retrieve military payloads, or worse. The result was a Soviet tendency to assume that any American capability concealed a military dagger, and in response, Soviet designers sometimes tried to build their own dagger first. In the 1960s, the Soviet Union created a program that, for decades, sounded like an urban legend: a military space station project called Almaz, associated with Vladimir Cholomet's design bureau. The idea was straightforward and frightening: put crewed stations in orbit for reconnaissance and potentially for military purposes, with the ability to photograph targets in high resolution and return that information quickly, not just via slow satellite relays. But what truly made Almaz infamous was the question that followed inevitably from putting humans in a military platform in orbit: what happens if an enemy tries to attack it? Here the Soviet answer was not subtle. At least one Almaz-derived station was armed. Salyut 3, launched on 25 June 1974, was publicly presented as part of the civilian Salyut program, but it is widely documented as an Almaz military station. It hosted a crew: Pavel Popovich and Yuri Artyukhin, who spent roughly 2 weeks in orbit. The station's true nature remained classified for years. Then, in the post-Soviet period, the world learned what had been mounted on it: a modified 23mm autocannon, the R-23M Carton, adapted from aircraft use for operation in space. A gun in orbit is one of those ideas that sounds cinematic until you remember what recoil means. Fire a cannon in microgravity and you are also firing the station itself, pushing it in the opposite direction. The engineering challenge is absurdly delicate: stabilizing aim, controlling recoil, managing vibrations, ensuring that nothing punctures something vital, and accounting for the fact that in space, even small debris can become lethal at orbital speeds. And yet, according to multiple documented accounts that emerged after secrecy eased, the Soviets tested it. The reported firing took place on 24 January 1975, after the crew had departed, with the station remotely controlled. Details vary in public sources, but the essential point is not in dispute. The cannon was fired in orbit. The experiment worked. The station survived. The concept of arming a space station was not a fantasy, it was a demonstrated capability. It's easy to laugh at the idea now, but imagine the mindset that produced it. This wasn't about showing off. It was about the fear that the next war might open above the atmosphere, and that hesitation waiting to see what the other side would do might be fatal. When you build a gun to shoot in space, you are not planning for peace. You are rehearsing for a world where the sky is no longer a sanctuary. But if Almaz represented Soviet paranoia, another set of experiments represented something different, a quieter kind of courage, driven not by the enemy but by the unknown. The Soviet Union's interplanetary program repeatedly aimed at targets that seemed almost designed to humiliate engineers. The most unforgiving of these was Venus. Venus is close to Earth in cosmic terms, and in the telescope it looks almost gentle, a bright bead in the evening. But it is a planet that punishes visitors. Its surface pressure is about 92 times Earth's, comparable to being nearly a kilometer underwater, and its surface temperature is around 465 degrees Celsius, hot enough to melt lead. The air is thick with carbon dioxide, and clouds of sulfuric acid hang above like a chemical warning sign. For decades, Venus was where probes went to die. The Soviets kept going anyway. The Venera program began early. Venera 1 was launched in February 1961, and contact was lost. That pattern continued: launch, hope, failure, learn, repeat. Each attempt forced designers to harden electronics, rethink parachutes, improve thermal shielding, and solve problems that had no easy precedents. In the West, space missions were often narrated like clean triumphs. In the Soviet system, many early missions were acknowledged only partially or not at all, but the work continued inside design bureaus where the cost of failure wasn't just professional embarrassment, it could mean political danger, budgets redirected, careers stalled. Then came December 1970. Venera 7 was launched on 17 August 1970 and reached Venus 4 months later. On 15 December 1970, it entered the Venusian atmosphere. The descent was a brutal test: thick air, immense pressure, heat that builds and builds. The probe's parachute system experienced problem sources, indicated deployed too early or tore, leading to a faster descent and a harder landing than planned. And yet, against expectations, Venera 7 transmitted data from the surface. For approximately 23 minutes, a Soviet-built machine spoke from the ground of another planet. In any other context, 23 minutes would be nothing: an awkward delay, a short phone call, a coffee break. Here it was historic. It was the first time in human history that a spacecraft had successfully made a soft landing on another planet and transmitted data from its surface, not just a flyby, not just atmospheric readings, a landing, a voice from a world that actively tries to destroy metal. And the Soviets didn't stop at a single fleeting success. They kept iterating. In 1975, Venera 9 and Venera 10 delivered the first photographs from the surface of Venus, black and white images of a rocky, broken landscape under a heavy sky. Venera 13, landing on 1 March 1982, returned color images and even audio recordings of wind. Consider what that meant technically: cameras and electronics protected inside pressure vessels, cooling strategies to delay heat death, drilling and sampling devices operating in an environment that would kill an unprotected human in seconds. It is one of the great underappreciated feats of 20th century engineering. It was also, in its own way, bizarre. A Soviet machine taking pictures on a planet where the air itself is poison and the ground cooks at temperatures that belong in an industrial furnace. The Venera successes changed planetary science. They provided direct measurements of Venus's temperature, pressure, and atmospheric composition, and they made clear just how extreme the greenhouse effect could become. In a century increasingly aware of climate and atmosphere, this was not abstract. Venus became a cautionary example written in data points and grainy panoramas, and it came from a system often dismissed as crude or blunt, yet capable of building one of the toughest robotic explorers ever made. Back on Earth, Soviet engineers were also tackling a different kind of hostile environment, the Arctic. The northern sea routes were not romantic in practice. They were grinding corridors of ice that could destroy hulls and swallow ships. For Russia and later the Soviet Union, the Arctic wasn't just geography, it was a strategic obsession. It offered access to resources, new shipping lanes, and military positioning, but it demanded power, endurance, and the ability to move through frozen seas for months at a time. The solution the Soviets pursued was almost shockingly bold: nuclear-powered icebreakers. The world's first nuclear-powered surface ship was the Soviet icebreaker Lenin, launched in 1957 and entering service in 1959. Lenin was not a weapon in the traditional sense, but it was a statement of capability, a civilian industrial vessel using nuclear propulsion to do a job no conventional ship could do as effectively. Nuclear power provided endurance. It meant an icebreaker could operate for long periods without refueling, pushing into the Arctic with a kind of relentless force that diesel simply struggled to match. There were problems. Early nuclear technology was dangerous, and Soviet industry could be unforgiving. Lenin suffered serious reactor-related incidents in the 1960s that required major intervention, including replacement of reactor components. This is where the story becomes complicated. Worked does not mean perfect. It means the concept proved itself, and the Soviet Union learned, adjusted, and expanded the fleet. Later, icebreakers like the Arctica class pushed the idea further. In 1977, the nuclear icebreaker Arctica became the first surface ship to reach the North Pole, a milestone that was both symbolic and practical, demonstrating Soviet reach into a region of increasing strategic importance. Nuclear icebreakers were a peculiar expression of Soviet priorities: massive, expensive, and tailored to a geography that shaped national identity. They also had long-term consequences. Russia remains, to this day, the leading operator of nuclear-powered icebreakers, a legacy of Soviet decisions. The experiment did not vanish with the USSR. It became infrastructure. Some Soviet experiments worked not because they were grand, but because they were relentless. One of the most important and, in its own way, one of the strangest, was the Soviet approach to human spaceflight endurance. For decades, the Soviet Union and later Russia treated long-duration space habitation not as a niche, but as a core competency, pushing cosmonauts to live in orbit long enough to turn the human body itself into a test subject for the future. The Salyut stations of the 1970s and 1980s, and later Mir launched on 20 February 1986, were not just platforms for national prestige, they were laboratories for survival. Cosmonauts lived in cramped modules that smelled of metal, plastic, and recycled air, surrounded by fans that never truly fell silent. They fought bone loss, muscle atrophy, and psychological strain. They dealt with equipment failures that in orbit could become emergencies. They performed routine maintenance that, on Earth, would have been a technician's job in a comfortable room, except they did it in a place where every tool could float away, every mistake could cascade, and the nearest rescue was not a helicopter ride away, but a controlled re-entry. These long-duration experiments worked in the most meaningful sense. They created a body of knowledge without which modern spaceflight would be crippled. When the International Space Station era began, it leaned heavily on procedures and experience born in Soviet and Russian practice. The Soviet Union's willingness to treat space as a place to live, not just visit, was a strategic choice that outlasted the state itself. But the Soviet story is never just about endurance. It's also about the breathtaking gamble, the projects that look, in retrospect, like they were built by a system racing its own decline. And this is where we return to Buran, because the spaceplane's automated landing was not a standalone trick. It was part of a response to something that had shaken Soviet planners, the American space shuttle. When the Space Shuttle Columbia first flew on 12 April 1981, it did more than signal a new era in American spaceflight. In Moscow, it triggered anxiety. The shuttle was reusable. It had a large payload bay. It could, in theory, launch and retrieve satellites. Soviet analysts worried, some sincerely, some perhaps opportunistically, that it could be used for military missions, deploying weapons, capturing Soviet satellites, or performing surprise operations. Whether these fears were realistic mattered less than the fact that they were believed by people who controlled budgets and strategy. The Soviet answer became the Energia-Buran program. Energia was a heavy-lift rocket, arguably one of the most powerful ever built, capable of launching massive payloads. Buran was the orbiter visually similar to the American shuttle, but different in key ways. It did not have main engines mounted on the orbiter like the US shuttle. Energia carried the main propulsion. And crucially, Buran was designed from the beginning with the capability for fully automated flight and landing. That design choice is one of those details that sounds like a footnote until you realize what it implies. Soviet engineers were not just trying to copy an American vehicle. They were trying to build a version that could fly without risking a crew, potentially making it more flexible for military tasks and reducing the political cost of a disaster. An unmanned orbital flight was a way to prove the system without putting cosmonauts on top of a new rocket on the first try. Yet even by Soviet standards, the program was a monster. The Soviet economy in the 1980s was strained. The war in Afghanistan, begun in December 1979, had become a bleeding wound. Oil prices fell in the mid-1980s, cutting into Soviet revenues. Mikhail Gorbachev came to power in 1985 and began reforms perestroika and glasnost that destabilized old certainties without producing quick economic miracles. The Soviet Union was trying to modernize, compete militarily, and manage internal change all at once. It was a dangerous juggling act, and into that environment came Buran, a program that required colossal resources, exquisite technical precision, and a stable industrial base. On 15 November 1988, the gamble was finally tested. The scene at Baikonur that day was not glamorous. The Kazakh steppe in November can be brutal flat land under a wide sky, winds that seem to have nowhere to go but into you. Energia rose from the pad carrying Buran. The launch was successful, and Buran reached orbit. It completed 2 orbits of Earth, one of those facts that sounds modest until you consider what was being proven: guidance, navigation, thermal protection, orbital maneuvering, re-entry control, and landing, all without a human hand on a stick. As the orbiter returned, conditions were not ideal. Crosswinds threatened the runway approach. Here was the moment where an expensive national symbol could become twisted wreckage. But Buran's systems adjusted. It made a steep controlled descent and performed an automatic landing on the Yubileyny runway at Baikonur. Ground crews watched a Soviet machine land itself from orbit. In the language of engineering, it was a triumph. In the language of politics, it was almost truly timed. Because Buran never flew again, the Soviet Union, so skilled at creating dramatic technological moments, could not always turn them into sustainable programs. The Energia rocket flew only twice, once with Polyus, a heavy payload that failed to reach its intended orbit in 1987, and once with Buran in 1987. By the early 1990s, the USSR was gone. The Buran program was cancelled, and its surviving hardware became a relic of a state that had disappeared almost overnight. In 2002, the collapse of a hangar roof at Baikonur destroyed the Buran orbiter that had flown in 1988 along with an Energia booster, killing workers in the process. The image is haunting, a machine built to survive re-entry from space, undone by the quiet decay of a neglected building. So why does Buran matter in a story about experiments that worked? Because it demonstrates something essential about Soviet technological culture. The Soviet Union could, when it focused, solve problems that were at the edge of what was possible: autonomous landing from orbit, nuclear propulsion at sea, armored probes on Venus, weapons tested in space, vehicles that flew like ships and sailed like aircraft. These were not paper projects. They were demonstrated, recorded, and in some cases operational. They forced the rest of the world to adjust its assumptions, and they did it through a distinctive method: massive state mobilization, competition among design bureaus, tolerance for enormous cost, and secrecy that hid failure until success could be unveiled like a sudden magic trick. Sometimes this system produced miracles. Sometimes it produced barishuls. Often it produced both in the same program. There is a temptation to treat bizarre Soviet experiments as entertainment, a parade of odd machines and stranger rumors. But the reality is more sobering. Each successful experiment had a chain of cause and effect that connected directly to human lives and geopolitical outcomes. The Ekrona plans were born from the Soviet Navy's desire to challenge American carrier groups and control coastal zones. Their existence shaped Western intelligence assessments and fed an arms race of countermeasures and new doctrines. The Almaz cannon was not a joke, but a symptom of a world in which leaders imagined war extending into orbit. It is a reminder that space militarization was not a future threat, but an active Cold War consideration. Vena's triumphs were not just technical stunts. They changed scientific understanding and demonstrated that the USSR could reach and touch other worlds with a toughness that was, frankly, unmatched for years. Nuclear icebreakers weren't just impressive ships. They were strategic infrastructure, enabling Arctic presence, an issue that, in the 21st century, has returned with melting sea ice, resource competition, and renewed military planning. And Buran, perhaps the most cinematic of all, showed that Soviet engineering could match and even surpass certain aspects of American systems, like autonomous control. It also showed something else, something darker, that a country can still achieve a technological miracle while the ground beneath it is cracking. What did the people inside these programs feel as they watched their machines succeed? Soviet archival culture and memoirs show a mixture of pride, exhaustion, and anxiety. Pride because the work was real and the obstacles were immense. Exhaustion because deadlines were political and failure could be dangerous. Anxiety because a successful launch didn't always guarantee a future. It could just as easily trigger new demands, new competition, and new risk. The Soviet Union was not unique in experimenting. The United States ran its own strange projects, from nuclear-powered aircraft concepts to mind control fears and spy gadgets. But the Soviet version often had a particular intensity, a willingness to commit to extreme environments, Venus, the Arctic, orbit, and to accept uncomfortable trade-offs because the alternative, in Soviet strategic thinking, was falling behind. In the years after the USSR collapsed in 1991, many of these projects became artifacts in museums or footnotes in declassified documents. Yet their influence didn't disappear. The Russian space program inherited Soviet habits of long-duration mission planning. Russian Arctic strategy still relies on nuclear ice-breaking capability that traces back to Lenin and Arctica. The very notion of asymmetric military technology finding a strange angle to neutralize an opponent's advantage remains a lesson drawn from that era. And there is another legacy, one that is harder to quantify but impossible to ignore. These experiments shaped how modern societies think about what is possible under pressure. When you watch Buran's unmanned landing footage today, it has a strange emotional effect. The images look dated: Soviet cameras, Soviet concrete, Soviet vehicles parked near the runway. But the act itself feels modern. Automated systems making decisions faster than humans. Algorithms guiding a massive vehicle to a safe landing. It resembles the logic behind contemporary autonomous flight, reusable rockets, and robotic exploration. In a world now filled with drones and autopilots, it's easy to forget how audacious that was in 1988. When you look at Venera's Venus panoramas, you see more than rocks. You see proof that human beings can push instruments into a literal hellscape and still receive a signal back still coax, meaning out of an environment that seems designed to erase us. At a time when planetary science is again surging and talk of Mars settlements fills headlines, Venus stands as a reminder: nature does not negotiate, and engineering triumphs are always temporary victories against entropy. When you think about a cannon firing in orbit, it forces a question that feels uncomfortably current. Space is no longer an empty stage for flags and footprints. It is crowded with satellites that run economies, militaries, and daily life. The Cold War dream of orbit as a battlefield never fully died. It simply waited for technology and geopolitics to catch up, and the Ekranoplan half-plane, half-ship feels like a ghost from an alternate future, a reminder that history is not a straight line of best solutions. Sometimes a technology works and still fades because it doesn't fit the economics of its era, or because the state that sponsored it collapses. Working is not the same as winning. That ultimately is what makes these Soviet experiments so gripping. They expose a tension at the heart of modern history. Human beings can achieve astonishing, almost ridiculous feats, but the systems that produce them can be fragile. A country can land a space plane automatically and still be unable to keep its supermarkets stocked. It can put cameras on Venus and still struggle to provide basic consumer goods. It can build nuclear ships to conquer ice and still be undone by political rot. The bizarre Soviet experiments that actually worked are not just curiosities. They are warnings and inspirations at the same time. They show what disciplined engineering can accomplish under extreme constraints, and they show how easily those accomplishments can become ruins when the society around them cannot sustain itself. In an age once again defined by great power competition, rapid technological leaps, and anxiety about what the other side might be building in secret, the Soviet 20th century doesn't feel like ancient history. It feels like a rehearsal, because somewhere in that wind-scoured runway at Baikonur, in that moment when an unmanned orbiter rolled to a stop after falling out of space, you can hear the real lesson humming beneath the triumph. The future is not guaranteed to the richest or the loudest, but to the systems that can turn strange ideas into repeatable reality, and then survive long enough to use them.